a number of domains of life where optimization is present and useful. This is another list. And funny thing, we will talk about knowledge discovery and machine learning as a different section of this lecture. This is why we start with optimization, because if you have this background of optimization, you will see that this approach to find the best solution actually exists in other fields of computer science, in other fields of artificial intelligence as well, even in artificial life or in life, in biology, you often look for the best solution. So it's good to have this background of optimization. Self-adapting computer programs, we will discuss one example later on. Okay, so this is a slide with many examples. And these are very specific, concrete examples of optimization problems. Let's think about this one, for example. Decide where to place pictures in the text. So you have some text, you have some set of pictures, and you have some references from text to pictures. Like usual, anything you write, and you have some diagrams, or graphs, or charts, or pictures, corresponds to this situation. And of course, you can place your pictures manually, but if you have references from text to pictures, you could think that there could be some algorithm that would, in a smart way, locate or adjust location of pictures in the text. So first question for you will be, what is the space or the set of all possible solutions? What would be a single solution?
Pause the video and try to answer this question.
Yeah, some formalization of where those pictures should go. So a single solution is like a single assignment of pictures to locations in text, and a set of all solutions is a set of all possible locations of pictures in text, right? And how to evaluate a single solution, because this is the last thing we need to employ our optimization algorithm is to know, or the computer needs to know how to evaluate those solutions and how to judge which one is better, which one is worse. So how to evaluate them? How would we evaluate whether one location of pictures is better than another location of pictures?
Pause the video and try to answer this question.
Because pictures have to fit to the text, right?
Yeah. When we have the text and some pictures, as I mentioned, we have some references. So on the second page, there is some reference to this picture, and on the last page, there is also a reference to this picture. So we have this information from which locations we refer to pictures. And we probably could use this information somehow to evaluate this assignment. What is the measure of the quality of picture placement in text?
Distance to the references.
Distance to the references?
But also the problem is if we have a lot of pictures and when we put one into the text, the rest of the text
flows, yeah.
We have new distances.
So we shouldn't do it like one by one, or even if we do it, we could consider it as a whole. But you mentioned that the distance from pictures to the references to those pictures, if we have like this, for example, the first picture is referred on the first page, but it's also referred to many times on the last page. Where should we put it? Towards the beginning, like on the first page, or towards the end? Yeah, probably, because this is what people expect. Even though like the center of gravity of those references is towards the end, we will still want to have pictures near the first occurrence of references, right? Okay, so we know how to do it in an automated way, so that humans do not need to put pictures in text manually. And of course, you have to consider a number of minor issues with the text, like those widows and orphans, and single lines somewhere that we wouldn't like to have. Do you know some program that does this for you? And you probably should know it. Yeah, LaTeX. And are you satisfied with how LaTeX?
Yes.
You like it. Most people actually are not satisfied with how LaTeX adjusts locations of pictures, and most people do everything to avoid this and put this enforcement to put pictures where they actually want them to be without LaTeX messing up. But you actually have to get used to LaTeX and get used to how it wants to adjust the locations, and then you are happy by giving some hints to LaTeX actually what you want and what you don't want, and you should probably avoid this unless you want to do everything yourself. Place bus stops in the best places. So probably you remember I talked about this difference between optimization and decision support. And I mentioned that in decision support we usually have the smaller number of solutions and you focus on humans. So this would be a good example of where decision support makes more sense. Because first of all, it may be difficult to formalize what does it mean to have the best location of the bus stop. You could probably try, but it's possible that human factors play a large role in this. And second, it may be that you don't have trillions or millions of possible locations. You only have 100 or 50. So it's a good candidate for decision support, to focus more on humans and do not try to formalize everything in the computer. Let's see another set. Is one more or no? Yeah. Satellites, create a chess program. If you wanted to solve this problem as optimization problem, create a chess program. A chess program is what plays a game, and a game consists of single moves. So what would be the single solution in this problem, create a chess program? What would be a single solution?
Pause the video and try to answer this question.
We always need to answer the same set of questions. What's the single solution? What's the set of solutions? And how to evaluate a single solution? So the answer is very simple usually. What's the single solution? The single solution is a single chess program. If we want to create, or if we want optimization actually to provide us with the best chess program, the single solution, so those circles here are chess programs, and there is a huge number of possible chess programs. What is a chess program? It's some strategy which takes decisions based on what the algorithm sees on the board. So it's a program. So we could think that a single solution is a chess program, or a single solution is a strategy, some algorithm that follows some strategy. Probably strategy is too strict, and it's better to speak about playing algorithms or playing programs, because they may have, a single program may have many strategies, for example, inside. Okay, so how to evaluate the quality of a playing program? Because we want the computer to do all this work. We don't want to involve humans. So how to do it automatically? Maybe it will help. What is the strategy of a program? Or what is a program that plays a game? It would be like, as an input, this strategy gets the board with some pieces, or maybe it's a card game, whatever. So it's an input. Then there is this magic we are looking for. This is this algorithm that plays. And the algorithm looks at the board and makes some decision where to put the next piece, for example. So this could be a set of rules. This algorithm could be a set of rules. If I see this on the board, then I should put my piece here. If I see something else, then I do another move. So we are looking for sets of rules. Okay, so this is more specific at least. We are looking for sets of rules, but again, the question remains how to evaluate each set of rules. because we want to put some number, preferably. Some number that would correspond to the quality, how good this set of rules plays a game. And we want the computer to evaluate this number. How to do it?
Pause the video and try to answer this question.
But it's tricky because you mentioned this other level, which we are not concerned with. You focused on what happens during the game, and we are not yet on this level, and we even don't need to be on this level. We only have some strategy, and this strategy somehow plays the game, and we want to know how good it plays the game. We want to get this number from the strategy. How much game it wins, but who is the opponent, or what is the opponent? With whom or with what this strategy will play the games. Because this is right what you said. How many games it won, but with what or with whom?
With another algorithms, strategies.
With another algorithms. And how do we get those other algorithms or strategies? We generate them somehow, right? Like those rules. Okay, so probably it would be very good to have humans as opponents, but we know we cannot do this, right? Because we have huge number of possible potential strategies. So unfortunately humans, even if we put our algorithm on the web, on the internet, online, so people can play against it, we probably won't get enough opponents. So the only option for us is to confront each strategy with some other set of strategies. Each of those programs will play against some other generated programs, and we will calculate the ratio of winning games for each strategy. And this has some disadvantages because we are operating on a closed world of strategies, but that's not the place to discuss this. Examples of NP-hard problems from my experience. So 4 examples. One is not very original because it's very similar to TSP. It's like a realistic TSP. When you have some tracks, for example, and why I say it's realistic, because, for example, there is something like time windows. So when you visit a location, you need to visit this location at specific time, like from 4 p.m. to 6 p.m. or something like this. So each location may have requirements as to where it wants to be visited. Then those trucks or those cars or whatever may have limited capacity. So you can imagine like delivery of some goods, like pizza, or for example, gathering garbage. So those trucks have limited capacity, so they need to return to some point to get new goods or to just give out all this garbage. And also those trucks may have different abilities, like each truck is different, not all drivers are the same. You could, for example, imagine medical staff traveling, and not every driver is the same, and not every driver knows the same. Or some technicians, for example, who are visiting those places to repair something that was broken. But this is still very combinatorial, and it's easy to imagine that you have this limited number of all possibilities. Then this is slightly less obvious, and I mentioned nature. When you are actually optimizing three-dimensional structures, so you are building something from this, and you are also optimizing control systems. So it's more or less like optimizing designs of robots. Instead of engineers building robots, you are considering each robot, which means each structure and each neural network, a single solution. So you have definitely a huge number of possible designs and possible solutions, and you are optimizing this. So this is a single solution to a problem, and you can imagine how many solutions there are. Oh, this is a fun example. I was developing a game, a sailing game, and sailing is not very easy. You actually do not need to do a lot because you are only controlling this rudder And if you have a single sail on your sailboat, you are only controlling the sail. You can trim the sail or you can just leave it. But still you have some goals. You want to sail in some direction, and there is wind, and you cannot control wind. Wind blows in some specific direction, so you have to adjust all those things. And initially, I implemented common sailing knowledge rules on what artificial intelligence, which was controlling the opponents in this game, what artificial intelligence should do to sail where it wants to sail. And I spent quite a lot of time trying to adjust various parameters of these angles of wind and so on. And still, artificial intelligence was noticeably worse than best humans. And I wanted artificial intelligence, those opponents, those bots in the game, to be challenging to humans. So finally, I gave up on these manual adjustments of all those rules. And I treated this as an optimization problem. So you can imagine that this sailing behavior can be formalized just as with games, as a set of rules, what to do in what situation. And I parameterized those rules, so I introduced some variables. And for me, a single solution was a single behavior of an artificial sailor, or this bot, which was controlling the boat. So this was again some set of rules with some parameters, and I wanted to optimize those parameters. And what would be the quality of the solution again? How to evaluate a single solution? Do you have an idea? I wanted those boats to be challenging for humans, so I created like 1 million of different environments with different boats, different wind speed and variability of wind. And those boats were simply sailing on those tracks, sailing tracks. And I was simply measuring time. And I was trying to minimize time, minimize average time over those millions of environments and islands and wind speeds and so on. And it was very, I was minimizing, for example, the number of capsizes, because those boats can also capsize if they are controlled improperly. And this was very successful. And this way I was able to obtain or to optimize very good strategies of sailing the boat. And there is no cheating in this game, which was quite an ambitious goal, like in most other games. So artificial intelligence in this game, in this particular game, cannot do anything else than a human could do. And it also doesn't have any additional knowledge like in many other games. So this is what makes this game challenging for artificial intelligence as well, not only for humans. Okay, and this is specifically, I mentioned this as another example of optimizing, like optimizing on a different level. Because I told you that you could optimize those three-dimensional designs and neural networks, like in robotics. So a single construction or a single three-dimensional design is a single solution. But in this example, a single solution is something else. A single solution is the entire world. So you could imagine that you have some artificial environment, and there are some parameters, like how much resources you have in this environment, like how much food in this case. What is the efficiency of ingestion of food for each creature? What's the distribution of energy in the world? And so on and so on. So I have like 11 parameters which describe each environment. And then I can create a large number, like, I don't want to put any number, but a large number of environments. Each environment is different. And I could look for a specific behaviors in the environment. And each environment has those creatures and some evolution inside. So it's like multi-level optimization, but I'm speaking now about this top level, when we are actually optimizing worlds or optimizing environments. So we are looking for 11 values, And this set of, like a vector of 11 values, defines conditions in a specific environment. Do you understand how this is done? So the solution is not a single individual or a single body and brain. It's the environment, one environment. So each circle here or each dot is the environment which is described by a different set of parameters, like more food, less food, more dense food, more scarce food, distribution of food different, and so on and so on. Okay, this is the homework for you. Pick a few examples that you like, for example, on these first two slides, and answer the same questions I asked you. What's the single solution? What's the set of solutions? How big is this set? And the most important, how to evaluate a single solution, because this is what lets the algorithm choose the best one. Why optimization problems may be difficult to solve? What are the sources of complexity for us if we wanted to optimize some problem? First of all, it may be the case that it's simply difficult to formalize a problem from real life. So this is what you remember, this picture when we had real life problems, models of problems, and algorithms at the top. So it may be difficult to do this, to formalize or build a model of a problem. Just life. A large number of possible solutions is this pure combinatorics, right? We remember these factorials and exponential functions. So this definitely makes it difficult if there are many solutions. This is again real life. It may be the case that this evaluation function, like for example, we mentioned this, how to evaluate chess programs. And you said that they could play against each other, okay? But this is very noisy or very imperfect information, because we probably cannot afford for each program, playing chess program, to play against 1,000,000 opponents. We will probably play against 100 randomly chosen, or maybe not random, maybe all the same set of opponents. So it's like a statistical sample, and if we picked some other set of opponents, again 100 opponents, but different opponents, we will probably get a different result. So it's just like a noise, like a random noise on this evaluation function. And this is what makes it difficult, because we always want to be able to tell which solution is better and which solution is worse. And if this function is noisy and imperfect, then we are not certain, like in this traveling salesperson, if we were not certain what's the distance between cities, and this distance would vary, like we often, when we use GPS, when we go, and we never know if there will be some traffic jam or something like this, then we cannot trust the evaluation function. So this is just real life difficulty. The set of feasible solutions is very limited. So I mentioned constraints, and I mentioned that constraints are bad. Constraints are something that limits the number of feasible solutions. Feasible is like allowed or acceptable solutions. So it may be the case that this space of solutions is huge, but most of it is restricted. We don't want this for some reason. So we have potentially a lot of solutions, but actually we have only a few acceptable solutions. Maybe not a few, because this space is huge, but still it may be like, for example, we have 10 to the power of 200 possible solutions and only 10 to the power of 5. So this is like a raw number of solutions, and these are only acceptable. So it's still a large number, but compared to this, it's like a tiny part of the search space. And unfortunately, this may be the case when we do not have a lot of resources. Imagine, for example, this timetabling example in some university. So there is somebody at the dean's office trying to build a timetable. And what happens if there is not enough buildings and not enough rooms? It's a very tight problem, right? It's not easy to put all those students groups to rooms so that there is no conflict, for example. So the less resources we have, the more constrained we are. And unfortunately, in real life, because of economics and economy, it's natural that this situation is so tight and restricted, because the university wouldn't have to buy buildings which wouldn't be used. So everything needs to be so tight and fully used, because this is where it's efficient. So it's again, these are like real life reasons that may and usually occur. Difficulty number 2, a large number of possible solutions. So look at this particular optimization problem. This is called SAT, and it's an abbreviation of Satisfiability. I probably mentioned this earlier already. So what's the definition of this satisfiability problem, of Boolean satisfiability? We have a number of logical variables. Each of them can be true or false, so it's a familiar ground for you. And we have some specific formula, like this F is capital F. And we are simply asking what values should have those variables so that this function is true. So it's a very basic logical question. What Boolean values should we assign to, let's say n, we have n variables, so that some given function is true. And let's think about this problem in terms of optimization. If we wanted to do this in a very naive way, using this exact algorithm, this brute force algorithm, what is the number of solutions, the number of all solutions in this problem, if we have n Boolean variables? It's again a combinatorial question.
Pause the video and try to answer this question.
What we asked on previous lecture.
2 to the n.
You say 2 to the n and
n to the n.
n to the 2? No? In mathematics, only one answer is correct. This is how it is in science. In most cases, you must be sure. N variables, each variable can be true or false. How many combinations of all the values of n variables? So it's 2 times 2 times 2 times 2 times 2. Each variable is to add 2 possibilities. And all of them are independent, right? So it's a very simple formula. So if we have 100 variables, we have already quite a large number of all these evaluations or valuations of those variables. What is ROADEF? It's an international, maybe mostly French organization which organizes competitions in optimization. I think it's every 1.5 years. And they usually take optimization problems from the industry, like from car companies or some space companies, usually from the industry. They make those problems public and they let everyone compete and devise the best algorithm. And they pay the winners a small amount. And then the companies actually implement those algorithms and earn millions of euros or dollars, saving costs. So in this example, I want to mention one particular case. I think it was from the Renault. So they had the assembly line when they are building cars, and they have a specification for each car. And cars can have different colors, different equipment, like, those audio equipment, climate control, and so on and so on. So each car can potentially be different, and they wanted to optimize the order of cars on the assembly line. In what order cars should be assembled to minimize the total time needed to build those cars. So if you are optimizing order, and you have, for example, n cars, you immediately should think about permutations. So the row complexity looks like n factorial. If you have n cars on the assembly line and you are asking only in which order they should be assembled. But this is why I mentioned that sometimes it is possible to reduce the space of solutions, because this looks really not nice. If you have 50 cars, for example, to consider in one batch, you would have 50 factorial. It's a huge number. But you could make an observation in this particular problem, for example, like it was in this case, that what takes the most time, what kind of operation takes the most time when you are producing those cars, and it turned out that definitely the most time takes cleaning those painting brushes if you change the color of the car, because the car needs to be painted in a different color, so you have to clean all this infrastructure, all those painting brushes. So if you know this, then you immediately, you could introduce some heuristic knowledge to this search problem, and you can group cars in the same colors, right? In batches of the same colors. Like you produce blue cars, then red cars, then white cars, black cars, whatever. And then you are only optimizing the order within each group and the order of groups. So this vastly reduces this row complexity, because you have only as many groups as different colors, like 5 or 6. And then some number of cars, like, I don't know, maybe it could be like 5 factorial times 10 factorial, for example, instead of 50 factorial. Just an example of, it's like a decomposition of a problem into smaller problems. And of course you may not be right, because this is all based on the assumption that cleaning those paint brushes takes a lot of time. Maybe the optimal, the shortest configuration and the shortest order could be that you really are swapping those colors within groups, outside of the groups, right? Maybe your assumption is not always correct, but it's in most cases correct, and this lets you save a lot on the complexity of the problem. Combinatorial optimization problems, it's some combination of elements. This is a Polish example of TSP. So we have this matrix of distances between each cities. This would be, this is not a good solution for TSP, because we are visiting one location more than once. So this is an example of an incorrect solution. And this is also an example of incorrect solution, even though it looks like we are visiting each location once. But it's not a single route. It's not a consistent single route. Okay, and this slide actually shows some numbers. You remember the examples from the previous lecture? I asked you about how many pairs there are, what's the number of subsets. By the way, I gave you this example, how many, if somebody wants to choose a set of features, how many sets of features there are, and you finally discovered this formula, and you see that this SAT problem, satisfiability, is exactly based on the same thing, right? So we are choosing variables that we want to be true. So it's the same formula. And you actually should note that we are operating on more or less the same set of formulas. We have factorials, we have exponentials, we don't have polynomials yet, but the more you deal with optimization, the more you see that you are operating on the same kind of approaches and formulas. Okay, so I give you the three examples. The number of pairs, the number of subsets, and TSP. So this is how TSP, the numbers of possible roots among n cities grows. So this is more or less factorial. By the way, there may be some mistake in this number. So you may look for the mistake. This is this number selection of a subset. So this is this formula. You may also check this if this is correct. But you see the difference between factorial and exponential. This is the difference between 2 to the power of n and factorial. And this is our nice polynomial. So we have this order of n squared. So when I mentioned, by the way, that we have 50 cars in a batch, so 50 cars, and we are looking for the optimal order on the assembly line, it's definitely not a nice number. Now I will show you a few famous examples of optimization problems, and you will notice that they often have these 3 or 4 or 2 letter abbreviations. We mentioned TSP, and I mentioned SAT, and now you have QAP, which is Quadratic Assignment problem. We have a set of locations, like buildings, and we have a set of like n buildings, and we have a set of functions or functionalities or roles, and we want to assign those roles to or functions to the buildings. So you could imagine that we are putting some groups of people in different buildings, and each group is specialized in doing something. And I will show you a graphical example later on, so don't worry, it's not like you need to understand everything at this point. But we are looking for the optimal assignment of people to those buildings, so to say. And what is optimal? We know the distance between buildings, so it's exactly like TSP. We know the distance between buildings, but we also know the flow or the intensity of flow or the intensity of interaction between those n groups of people or n roles. So this is, you probably now feel what we want to optimize here, or what we want to minimize. We want to minimize the overall flow. So we don't want people who interact a lot to be located far away, because this would increase this multiplication or this product of distance and flow. So it's like a generalized TSP, or TSP with some other additional layer of difficulty. Graph partitioning problem. We have some graph, and we want to partition the graph. So cut into separate pieces. We want to separate the graph into parts. And how do we want to separate the graph? This time it can be any graph, so it's not like TSP. And we simply want to cut the graph into a number of independent parts, but we want to cut through the lowest number of edges. So like we want to minimize the destruction of edges. And again, you could think that you have a group of people, and people are interacting, and unfortunately you need to split them into 2 parts, like a company is splitting into 2 different buildings in different cities, for example, and you want to minimize this destruction of interactions. So how to cut a graph like this? Okay. Graph bisection. Well, actually, graph bisection and graph, what was earlier, graph partitioning. Partitioning is like more general, and bisection is like we are saying that into 2 parts, into specifically 2 parts. And you can see this green ellipse or green circle shows you one part that you take away, And these red edges are the edges that you need to actually cut. So if you take 1 and 3 from this graph, you preserve this connection, this edge, and 2 and 4 also have this connection preserved, but you are breaking those 4 edges. So the question is whether you could find another bisection of this graph to save more connections, and to break a lower number of connections. Okay? Knapsack problem, or rucksack, knapsack problem. A very, very popular problem and very practical. And the name is very appropriate in this problem. So you have your knapsack when you are going again on some trip, and you have a number of elements. Elements can be larger or smaller, and this knapsack has a limited capacity. For example, it could be in kilos or in pounds or whatever capacity. And each of those elements has also some capacity, like W1, W2, W3, W4. So you cannot put all the elements or the items in this knapsack. They will not fit. But each of those elements, those items, apart from their size or weight, they also have some value. I will use C for value. So W1 and C1, W5 and C5. And you want to maximize the value of items in the knapsack. But you cannot exceed this capacity. Okay? So it's really very elegant optimization problem. Here is this example of investments. So for investments, this capacity of the knapsack would be simply your money, the amount of money you can spend. And this is like what you can buy. You cannot exceed weight. Weight would be the price of things that you buy. And C would be some value for you of those things, how useful they are for you. So you want to maximize the usefulness of things. So this is the list of those most common problems with abbreviations. There is even something like a compendium of NP optimization problems. So it's like a classification, and we have some groups like problems with graph theory, network design, set of partitions, and so on. So it's like a general classification of all optimization problems. And you can zoom in, look closer at some category like network design. So let's zoom in. And this is network design. You have these subcategories. And here you have specific optimization problems. Like in routing problems, the first one is actually our TSP problem. But here you can see, for example, longest path. So this is like shortest path, and this is like longest path. So it's like a reverse traveling salesperson. Somebody who wants to visit all the cities in the longest possible route. Like some taxi man, maybe, who wants to get the most money out of you, and there is some visitor from some other country who doesn't know the city. It's a good opportunity to earn a lot of money. Oh, I will show you the examples of spanning trees as well. Even more, okay. So this is an example of a spanning tree. What is a spanning tree? Again, we have some locations, and we have some costs of connections. So it's more or less like a TSP when you have distances. Distances can be proportional to costs of building a connection. And your goal is to connect all the points in some consistent network or graph, but minimizing the cost of building this network. So for example, something like this would do, because all the points are already connected, but maybe some other configuration of connections would be also good. Okay? So you see how generally are those optimization problems formulated. It could be like building a computer network among some points, but it could be some radio network or maybe pipes, some water pipes. Like you have houses and each house needs to have electricity and water. So spanning tree. Vehicle routing problem. I talked about this, so we'll not talk even more. I even talked about those examples of capacity and time window. This is a very practical problem. Project scheduling problem. How this problem is formalized and what's the model of the problem. We have a set of activities, A1, A2, A5, and this is some kind of constraint, like precedence constraint. And this edge and this arrow means that you cannot start this activity before this one is finished. So you cannot start A4 before you finished A2. You cannot start A3 as well before you finish A2. So each arrow is a constraint of precedence. And what you usually are interested in is to order those activities so that the finish time is the shortest. So the last activity finishes as soon as possible. This is usually like a default criterion of optimization, but of course you could also always consider cost. So maybe you want to have the shortest and the cheapest and maybe also quality, because we know from building motorways in Poland that the cheapest and the shortest is not necessarily acceptable after a few years, for example, when the quality was very low. So this is what I mentioned. This is like a project scheduling problem, but the first part of this title says resource constraint. And resource constraint means that you don't have a complete freedom of where to start and when to stop each activity, because each activity requires some resources to work or to do. As an example, you can have in your mind some complex building enterprises, like building motorways, building cities and things like this, or parts of cities, or huge buildings. So you have a lot of activities, right? You have a lot of engineers working on some specific problem, but also if you work in any company, even in a software company which writes software, you have programmers, but you have also testers and beta testers and some managers and people who test the market and do some tests on humans and so on and so on. So actually every product, the development of every product could be expressed in a similar kind of a graph. So the more complex is the product, the more gain you will have from employing optimization. Of course, in real life, we mostly have very simple problems and we do not think about our life in terms of the project scheduling problem. But if there is some company and the company really wants to minimize cost and maximize profit, they should employ this optimization approach. Two-dimensional packing problem and packing problems are also quite intuitive. It is maybe similar to this backpack problem or knapsack problem. So we have a set of items and you simply want to fit them in the smallest space. And now we have